Okay, I will start then. My name is Marcos Basso, and I will present a work that I developed with my advisor called Jonas Maziero, and is called Quantitative Wave-Particle Duality from the Density Matrix Properties. First, I will give the motivation of our work, then I will go through the double slit and the density operator. I will talk a little bit of measures in quantum information and how to use them to quantify complementarity. So, both the uncertainty principle and the complementarity principle was guidelines to the development of quantum mechanics. However, just the first, the uncertainty principle, was put in a quantitative form right from the beginning and became known as uncertainty relations, and it follows directly from the mathematical structure of quantum mechanics. And it does not depend on a thought experiment or a particular physical scenario like the Heisenberg microscope, that it's a particularly uncertainty relation between momenta and position. These uncertainty relations work for any observables. On the other hand, the complementarity principle was put in a quantitative form just recently, from the 90s to here. However, it's common always to use some particular example, physical scenario, to derive these complementarity relations. So the main idea of our work is to derive these complementarity relations from the mathematical structure of quantum mechanics. So to begin with, just to give an example, the double slit is a well-known experiment, and the state of the system of the particle after the two slit is given by a superposition of both paths, and is represented by a state vector in the Hilbert space, which is given by the first equation. While the probability of finding the position of the particle in some y coordinate in the screen is given by the famous Born rule. Then you can, from the probability, you can define measures of the wave and particle aspect of the system. For instance, the visibility is defined as the difference between the maximum intensity and minimum intensity. That can be written in terms of probabilities, and is a measure of the wave aspect of the system. We can think as the contrast of the interference pattern, while the predictability is just the modulus of the difference of the intensity of one slit and the other slit. So if one slit is more intense in certain sense, so it has more probability of the particle went through that slit, the predictability is bigger, and so it's a particle aspect. However, the state vector in the Hilbert space is not the most general way to represent the state of a quantum system. This is done by considering the density operator, which includes both classical uncertainty and quantum uncertainty, because when you are working with a state vector, you're always sure about the preparation of that system. And in reality, or in an experiment, this is almost never reached. So the density operator is characterized by being Hermitian. It has trace equals 1, and it is posit semi-defined. The diagonal elements describes the probability of a certain state being populated, And it's worth mentioning that the diagonal elements is a classical probability distribution in the sense that all diagonal elements is between 0 and 1, and the sum of all of them is equal to 1, just because the trace is equal to 1. While the off-diagonal elements of the density matrix of the density operator describes the effect of interference between the state I and j, for example. So you can define also predictability and visibility using the density operator. For instance, if you consider a Mach-Zehnder interferometer, the predictability can be calculated as the mean value of one of the Pauli matrices. And when expressed through the elements of the density operator, is just the modulo of the difference of ρ11 and ρ22. For instance, ρ11 is the probability of the particle being in the path 1 or the state 1, while the visibility is just the modulus of the interference of the two states, which you call coherence. So from these two definitions, you can derive a complementarity relation, and this was done for the first time by Engler in the 90s. Since then, it has been a lot of developments to quantify the complementarity principle. One of them was made by Durr, he established minimum criteria that any predictability and visibility measures should satisfy to be considered a good measure, because in this time the measures was only defined, it was not derived, and it always considered some particular example. So the criteria are basics. The first two is just basic. For instance, D3, you can read like if the path of this, if the path is known or the state of the system is known, then predictability must reach its maximum value and visibility should reach its minimum value. Otherwise, if all the states are equally probable or all the paths are equally probable, then P must reach its minimum value. In addition, if rho is pure, which means that you can express the state of the system as a vector in the Hilbert space, then V must reach its maximum value.
2 minutes.
Okay. And also P and V must be a convex function, because classical mixing does not increase in neither of the two measures. Also, with the development of the quantum information science, it was suggested that quantum coherence is a natural generalization of visibility for any level system, not just a two-level system as the Mach-Zehnder interferometer. So why consider quantum coherence as a natural generalization of visibility? Because they quantify the superposition between orthonormal states, and one of the ways to measure quantum coherence is given by the distance between rho and the closest incoherent state, which is the state that has no superposition. One of the ways is using the Hilbert-Schmidt norm that defines a distance in the space of matrices, and we can obtain equation 1. Also, it's worth mentioning that there is several measures of quantum coherence based on entropy or based on other distance. So for a two-level system, you have the expression below, which is very similar to the expression for the visibility. You can write one in terms of the other. Also, another well-known measure in quantum information, in certain sense, in all other areas of physics, is entropy. In information theory, in particular, the entropy quantifies the lack of knowledge of a random variable before its measurement. In this case, the random variable is the state of the system or the path of the system. So our idea was to use entropy to quantify predictability, because if entropy quantifies the lack of knowledge before its measurement, minus the entropy in certain sense quantifies our capability to make a correct guess before its measurement. So by exploring one of the properties of the density matrix, which is given by equation 2, which can read as trace of rho square is less or equal than 1, it was possible to derive the inequality tree, which is an inequality between quantum coherence, linear entropy, and von Neumann entropy. So just to emphasize, we obtain equation 3 within equation 2. And this is just a generalization between the off-diagonal elements of the density matrix and the diagonal elements. So from equation 3, we motivate to define the predictability as the difference between the maximum of the entropy and the entropy of row diagonal. And from these equations, it was possible to derive the following complementarity relations, 7 and 8. Also, these images is to verify that random density matrix satisfies the inequalities derived. So to conclude, by exploring the density matrix properties, it was possible to define predictability in terms of entropy and quantify complementarity from the mathematical structure of quantum mechanics, or the properties of the density matrix. And we did this same procedure for all other measures of quantum coherence, just to emphasize that what matters is the procedure and not the measures. So I finish here.
Okay, thank you. Questions? Perguntas?
Vamos usar para aparecer vocês.